Hello and welcome to another episode of Chemistry Chats with Cochrane. Today we're looking at some complex calcs with mixed stoichiometry. And so what that means is we're going to be looking at how we can use complex gas calcs in the context of mixed stoichiometric problems, i.e. I might have something with a mass of a substance and I need to calculate some volumes of some gases. So we've got here, consider again the Haber process. In one such scenario, a desired production of 4 tons of ammonia is required. Given the reaction occurs at 500 degrees Celsius and a pressure of 35 megapascals, calculate the volume of both hydrogen and nitrogen required to produce this amount of ammonia. Now, important for us to understand, of course, that we are in the midst of a series, and so we have recently dealt with the Haber process. But let's say we were to get this question in an examination, we can actually answer this question whether we know what the Haber process is or not, because we are told that we have a desired production of ammonia, and we are calculating both hydrogen and nitrogen. So we know that this is some kind of reaction that involves hydrogen and nitrogen in order to produce ammonia. We don't know what else is in this equation potentially, but we can now balance that and we can still get a ratio of everything that's in here. One of the hardest parts about chemistry is being able to take limited information and think, how can I use my own chemistry understanding to make this make sense? So because we've got the word production there, we're going to write an equation, which we have done. So we've got 3H2 plus N2 to produce 2NH3. Now, our little question here is telling us that in one such scenario, 4 tons of ammonia is desired. Oh, I should put a love heart around that because it's desired. This is what we desire. This is what we would love. But we don't get that. That's not what we're asking. We're asking this. These bad boys are at 500 degrees Celsius and at a pressure of 35 megapascals. And we are trying to use this information to calculate the volume of each of these gases. So, step 1 in any kind of lovely kind of problem like this is we need to list our knowns and unknowns. So let's have a quick confirmation. What do we know? Well, we know our mass of ammonia is equal to 4 tons. Now, of course, we don't like tons, so we do 4 times 10 to the 6 grams. Excellent. We know our molar mass of ammonia. What is our molar mass? It is 17.034. We know the temperature, which is 500 degrees Celsius. But of course, 500 degrees Celsius is not good enough for us. We need to add 273.15 to get that into Kelvin. So this now becomes 773.15 Kelvin. We know our pressure, under pressure, 35 megapascals, which is 35,000 kilopascals. Fantastic. Anything else? Oh, gas constant, 8.314. We probably need to write that down because it's in our data sheet, but it's always helpful to have kind of in front of us. So we have now written down all of the information that we have available to us, and we can now begin answering our question. Now, again, we haven't done any work at this point, but we have put ourselves in a place to succeed because we've seen everything that's available. We know the equation, we know the values, we know everything that is going on. So let's think to ourselves, what is the substance that we know most about? Well, I'm going to make the argument that we know most about ammonia. The reason for that is we have both a mass and a molar mass, which means I can use N equals M over M to calculate my number of moles. In this circumstance, that will be 4 times 10 to the 6 divided by 17.034. And if I chuck that in a calculator, I get the very small number, 230. Sorry, I'm going through a tunnel. I'm losing. Sorry, I don't know what happened there. Just ran out of signal or something on the phone, not sure. 243, whoa, what the hell? 234,824.47 moles. Has a science degree, can't read simple numbers. Okay, so we have the number of moles of ammonia. Oh, we forgot to include that in our working. That's poor, sorry. Hope you haven't been following along. Number of moles of ammonia. Sorry, there we go. Now, we've got a number of moles of ammonia, and we've got to calculate a volume of both hydrogen and nitrogen. So we've got to go from here to here. Now, of course, that means we need to do our stoich. So I'm going to say that my number of moles of N2 is therefore 1 on 2 times by the number of moles of NH3. Use the nuke to do that. I'm not going to bother rewriting that number because that's a considerable amount of work for me. 117,412.23 moles. Now, just a note on this, we want to be clear to our marker that we understand that this is a stoichiometric ratio, so that they are clear, that we are clear what we are doing. Okay, second thing then, we can also calculate our number of moles of H2, which of course is 3 on 2 times by the number of moles of ammonia due to stoich. And that will give me the number 352,236.7. Fantastic. Okay, but that is unfortunately not what the question is asking me. The question is asking me for the volume of these things. And so now I need to ask myself the question. Volume, I have two options. This could be a solution, but these we know are both gases. So it's not a solution. What's our only other option? Is that it's a gas. Now we need to ask ourselves the question, is this gas at STP? No, it's not, because it's at a very high pressure and it's at a very high temperature. So therefore, we must be using the equation PV equals nRT to calculate volume. Let's rearrange that to get V equals nRT on P. Okay, so now we can calculate our volume of nitrogen really simply, really easily, right? We can just chuck in a little bit of N, which is this number here, I can't be bothered rewriting it, multiplied by 8.314, multiplied by 773.15, all of that divided by 35,000. What do I get? 64,690.5 litres of nitrogen. That's quite a lot. Let's do the same now for H2. Of course, everything is the same in the calculation of H2. The only thing that's different is our number of moles. I'll write it out fully this time so that everyone's on the same page. 236.7 multiplied by the universal gas constant 8.314 and the temperature, which is the same, 773.15. I'm going to divide all of that by 35,000 because that's my pressure. A reminder, this is the equation I'm using down here. It's also the equation I'm using down here. And if I chuck all that in a calculator, I get 21. Oh, I've shanked these numbers. They're the wrong way around. I'm so sorry. This was actually the volume of... Whoops, sorry. I'm so sorry. But I'm committed. I'm too far into this video to go back and repeat it. So, sorry. Whoopsie daisies. That's that one there. And that's not that one. Oh no, I've made a terrible mistake. Oh no, it's all going... Oh, it's terrible now. Volume of H2 is actually 64,690.5 litres. I'm so sorry that I got that wrong. I've worked it out differently on my bit of paper in front of me. But now we've answered that question, complex mixed stoich. Very good. Okay, next one. We're going to consider the reaction of aluminium carbonate with sulfuric acid. In one such reaction, a sample of 4,510 grams of 65% pure aluminium carbonate reacts to produce an unknown volume of gas at max atmospheric pressure and temperature of 33.5 degrees Celsius. Calculate volume of gas. Jeepers, there's just red lines everywhere. I should have proofread this before I put it on the internet. Okay, so we are considering this reaction here. Wait, let me change colors so we've got some consistency. We are considering the reaction of aluminium carbonate with sulfuric acid. So this now, obviously is no equation given to us, but we now need to think to ourselves, what is the reaction of an acid with a carbonate? Well, we know that the acid, H2SO4, is going to react with the carbonate, aluminium carbonate, Al2CO3. And these bad boys, sorry, just real quick, how did I get this formula? This is something I know that some of us have been struggling with. How did I get to this formula so quickly? I didn't even think about that. This is what I did. I have Al3 positive and I have CO3 2 negative. These two charges don't balance. Two ways I can do it. Firstly, I can swap and drop my charges to get Al2, CO3, 3. That's more than okay. Or I can balance the charges, up to you. But that's how we get to that formula really, really quickly, really simply. Now, I'm going to produce a salt. And by salt, I mean ionic. In this circumstance, it's going to be a metal with a non-metal. This aluminium is already attracted to this non-metal. It's looking for something new on the town. The only thing that's new is this guy. It's not going to be attracted to H because that's positive just like it. So I know I'm going to produce some aluminium sulfate, Al2SO4 3. That's my salt. Whenever I react a carbonate with an acid, it is also a neutralization reaction. What is the most neutral of all? H2O and then all that's left is my unknown gas of CO2. Is that balanced? No, it's not. Let's chuck a 3 in front of that, and a 3 in front of that, and a 3 in front of that, and now we have a balanced chemical equation. In one such reaction, a sample of 4,510 grams of 65% pure aluminium carbonate. Okay, let's write this down. We have a mass of aluminium carbonate. I think that's important. That is equal to 4510. However, it's at 65% purity. So that means only 65% of it is actually usable. So if I was to times that by 65%, I get 2931.5 grams. So I've got that much mass of aluminium carbonate. Would you agree with me that I can also calculate my molar mass of aluminium carbonate by doing some maths? Al2CO33. Add all of those molar masses up of all of those elements, and I get 233.99 Gmol, -1. Excellent. Is there anything else my question tells me? It's an unknown volume of gas. Okay, so I'm looking at the volume of gases. It's atmospheric pressure. Ooh, hang on. I don't have a perfect memory. I can't remember atmospheric pressure. Oh, how do I work this out? I check the data sheet. The data sheet tells me atmospheric pressure 101.3 kPa, and a temperature of 33.5 degrees Celsius. A nice balmy summer's afternoon. We need to calculate the volume of gas. So we know very clearly this is not an STP calc because it's not a standard temperature, even though it's standard pressure. So we know that we are likely to use the formula PV equals nRT. Okay, so I've done my pre-work. I've got everything, all my ducks are in a row. That's all my stuff. Now I need to try and work this bad boy out. My first step, of course, is going to be to calculate the number of moles of what I know most about, which in this circumstance is Al2NOC. 2931.5 divided by 233.99 gives me 12.5283 moles. How did I get this? Just real quick, so we're all on the same page. N equals M on M. Now I've got my number of moles of aluminium carbonate. Absolutely fantastic. I can now use Stoich to calculate my number of moles of CO2. How do I calculate my number of moles of CO2? Coefficient in front of CO2 divided by the coefficient in front of what I know about. So that's 3 on 1 multiplied by 12.5283. Chalk that in a calculator. I get 37.585 moles. There we go. Now I've got my moles of carbon dioxide. I can now rearrange my equation to get my volume of carbon dioxide by saying V is equal to nRT on P. If I chuck all this together, I get 37.585 from my number of moles. I get 8.314, which of course is my universal gas constants. Multiply that by the temperature, which is 33.5. Wait, hang on a second. No, it's not. Because temperature is only ever done in Kelvin. So that means temperature must be 273.15 plus 33.5. Sneaky. Now, just a reminder, you can always do this in your calc like this, like I'm doing here, but give me an R, give me an I, give me an S, give me a K, give me a Y. That is risky, because what if you forget? I don't forget because this is my job. You might forget because you're still getting good, but when you're really good, not that I'm really that good, as you guys can all already tell, but it's probably just a bit risky. I would just keep it up. I'd just do it at the beginning. I just didn't in this circumstance because I forgot to. There we go. There's our volume of CO2. So this is a good example of a purity calc with mixed stoich and having to write an equation. I think that's it. We'll stop there for today, and then we'll do a little bit more of another video, and that other video is going to be on a bit more complex stuff. Fantastic.